Hey guys, I decided to film a couple of videos in the same day, but guys, it is warm out here, so I may just put my sunglasses on to teach this lesson. I'm totally kidding. I'm not going to do that. All right, let's get in here quick. Let's do our second day of section 16-2. Let's just get right to it. So here we go. Here we go. So we are, in fact, going to be doing another sort of like just a bite-sized bit of 16-2. So remember, we tried to divide up 16-2 so that it was manageable for us, right? We didn't have to worry about doing big pieces of information. And so this is our second day. There's going to be a third day tomorrow. So the questions that you're going to do in the homework are sort of like centered around these topics, okay? So we're kind of just going to jump right in here. So yesterday when we did yesterday, I guess, in our previous lesson, you did sometimes you can just plug in the number. We learned all those great little limit rules, right? Like the limit of a sum is the sum of the limits. The limit of a product is the product of the limits, like all that good stuff. And then we just realized that you could just plug in the number and boom, golden. We learned about when you have infinity, that you should try to make one of them go to like zero, some of the terms, so you can make those go away. So right now, what we want to consider a special type of function, okay? So all of these are going to be like special types. We're going to do like 3 examples today. Yes, I know, so amazing for just 3 examples. So what happens if you want the limit at a particular value, but that value makes the function undefined? Oh, how would we do that, right? You're like, oh no, if I plug in that value, it makes it be like something over 0 or 0 over 0. And you're like, that does not make any sense mathematically. So what can we do with that? Okay. So the limit may not exist. That actually could be the answer. The answer could be, oh, the limit does not exist. Or, and here's where you're like this. Super exciting. You may be able to work some algebraic magic. And I wouldn't really say like magic, but just like do some algebra, like factoring or something like that would be able to make it work. So let's dive right in and do some of these examples, okay? So example number 1 right here says find the limit. All of the examples today are going to be find the limit. And this find the limit says we're going to do the limit as x approaches -2. And our function is x plus 3 over x plus 2. Okay. If you plugged in -2, if you went ahead and substituted and just plugged in a -2, this would be like a problem. Okay. You can't factor this. If you like plugged in -2, where's my pencil guy? Pencil guy, where'd you go? Okay. If you plugged in -2 right here, this would be a 0 on the bottom. You would get something like, for this example, you would get like no, you just get 1. You would get a 1 over a 0. And you're like, that does not make any sense. You can't have a 1 over a 0. Okay. So what are we going to do with that? Well, maybe we should think about what the graph looks like, or maybe we should try to factor it. Okay. So we can't factor this. X plus 3 is an x plus 3. X plus 2 is an x plus 2. But maybe we can think about what its graph looks like. Okay. And I know you're not graphing the whole thing, but you know what this graph does have? Like if you wanted to, you could pull up Desmos, or you can just kind of think about this in your head. We did graph these like way back in first semester. Yeah, first semester. But remember how if you have x plus 2 on the bottom, there's an asymptote at x equals -2. So this is like 1, this is 2. There's an asymptote. Oh, goodness gracious. That is the ugliest asymptote I've ever seen in my life. Okay, so you have like an asymptote, and then you try like, you could graph it. So because there is an asymptote, and because this graph like swoops in 2 different directions, okay? In fact, I'm going to graph it I have my phone right here. I'm just going to pull up Desmos super quick just so I can see what this graph looks like, just to confirm. So you might want to do the same thing. So I'm going to do a parentheses. I'm going to do an x plus 3, close the parentheses. I'll divide by an x plus 2, and just confirming what the graph looks like. It looks kind of like this, and like, whoops, a little bit like this, okay? And so definitely this has right here an asymptote, but because it did not say from the right or from the left, and we're just looking at this, when you come in from the right, it goes way up to positive infinity. When you come in from the left, it goes way down to negative infinity. Folks, that is not the same thing. That is like a mess. And so what we're actually going to say on this one is that the limit does not exist. Okay. So on this one, because one of them is going to positive infinity, one of them is going to negative infinity, we're going to say the limit does not exist. This is one type of question that could happen if it truly does make it weird and undefined and you're like, oh no. Okay, well, what's another type of question? So here's another one, and it says the limit as x approaches 2, and it says x squared minus 4 over x minus 2. So if you're looking at this guy and you decided just to straight plug in 2, right? Like that could be fun. Like, yeah, plug in 2. You would get, 0 divided by 0. And that, folks, is 100% mathematical nonsense. Okay, so you have to now think to yourself, there's got to be another way that I can do this question. And yes, there totally is. I'm so excited. Okay, what you can do is you can factor this one, and that should be your algebraic choice, okay, is to do some factoring. So on the top part, we're going to go the limit as x approaches 2. We're still going to write that again, but we're going to factor the top. So the top can factor. That's a good old difference of squares. I do love a difference of squares. I know, they're one of my favorites. And we get x plus 2 over x minus 2. And then wouldn't you know it, the x minus 2's cancel each other. And all this boils down to is the limit as x approaches 2 of x plus 2. Hey guys, guess what? You can plug in 2 now. I know, so exciting. And you just get an answer of 4. And so this guy has an answer of 4. Okay, if we graph this on Desmos, what this would actually turn out to be is a line of x plus 2. We would have a hole in the graph, but it would be approaching at like the from the right and from the left would be approaching a y value of 4. So this is an example of something that's definitely mathematical nonsense. When I first plug it in at the beginning, I got a 0 over 0, and that's like blech. But then actually it's more like this. That's better. And then you could factor this one. So you factor, and then the result, you go ahead and plug in the 2 and you get an answer. Or so remember, guys, it's actually undefined there. Okay, just side note, right? The graph is not defined at the value of 2. There is a hole in the graph. It doesn't work. It's just as you come in from both sides, the y values are approaching 4. Okay, just trying to make that connection between the picture and also the mathematics. Okay, we're going to do one more example, just one more, and it's another one of these where we can factor. Okay, so this is part C. This is our last example, and then we're going to write some extra little fun things. This says find the limit. So we're going to take the limit as x approaches 3 of x minus 3 over x cubed minus 27. So if you were to plug in 3, do you know what we would get for an answer? We would get 0 over 0, and 0 over 0 means nothing to us. This is mathematical nonsense. So the answer is not 0. It's just like, oh, I have to do something else, okay? Because this is like, bleh, this is nonsense. So we can recognize that this right here is factorable. It's actually factorable to a difference of cubes. I know, so fun. So we're going to write the limit as x approaches 3 again. The x minus 3 is going to be on the top, and then we're going to do like that song, right? So you say, take the cube root of the first and the cube root of the second. Keep the sign. So you got x minus 3. Then you square the first, so x squared is squared. Multiply together, 3 times x is 3x. Square the last, 3 squared is 9. And then you say soap. Remember, this was the same sign, the opposite sign, and then always positive. And wouldn't you know it, the x minus 3's totally canceled. Goodbye, x minus 3's. Nice knowing you. We simply get a 1 over x squared plus 3x minus 9. And now I can go ahead and just plug in 3, and it's going to work because the problem is now been taken care of. So if I plug in 3, that's going to be a 3 squared on the bottom. So 9 plus a 9 minus a 9. And 9 plus a 9 minus a 9 turns out to be 9. So fun. And so the answer is 1/9. So our answer to this question is 1/9. All right, ladies and gents, we want to write some things down just to make some connections. One of the most important things about mathematics is that we don't learn things like a tunnel vision and you're like, I can't see anything else. We have to think about all the mathematics, okay? So back in the day, first semester, we were talking about sort of like those, like graphing these things. And so the graphs have relationships to these limits, okay? And so the horizontal asymptote rules and your limit rules are going to complement each other. It is kind of amazing, okay? So your horizontal asymptote rules and your limit rules complement each other. Let's write some fun facts down, and then this will be it for notes. So if you're looking at a polynomial, okay, or you're looking at like a what am I going to try to say? Like a rational expression where you have like a polynomial on top of a polynomial, you're going to think to yourself about the degrees, okay? If the degree of your f of x equals your degree of the f of x, your limit is going to be the ratio of the leading coefficients, okay? So your limit is going to be the ratio of the leading coefficients, which is also known as basically the horizontal asymptote. We did one of those examples yesterday. If the degree of the top is going to be less than the degree of the bottom, right? So this is when you have like your f of x is going to be on the top, and then your g of x function is going to be on the bottom. So if your f function has a smaller degree, so the top is smaller than the bottom, then the limit is 0, and the horizontal asymptote, okay, is at, okay, it has a horizontal asymptote at the x-axis. And then if your degree of f, basically your the top is greater than the degree of the bottom, you are not going to have any asymptotes at all. The limit is going to go to a positive or negative infinity. Those numbers are just going to get really large or really small, and there is no asymptote. Ladies and gentlemen, it is nice to make connections, don't you think? I know, I love it so much. I mean, mathematics for the win. Like, isn't that amazing? So this kind of like algebraic stuff is what you're going to practice, where you're going to do some factoring and all that good jazz. Okay, so your homework for tonight is just to do 10, 11, 12, 13, and then 21 through 19 doesn't make any sense. Mrs. Fox, I think it's 21 through maybe 29. Oh my goodness, Mrs. Fox is a crazy person. Let me look that up right now in this pre-calc book. Oh my goodness. Scramble me up. What is Mrs. Fox thinking? Let me get to the right page. Someone did not do a typo on that. Oh, yes, it is through 29. So let's just cross that off. My bad, my bad, my bad. We are going to go through 29. Silly Mrs. Fox, silly. I can't believe that lady. She's crazy sometimes. So you're going to do 21 through 29. All right, peeps, that is the extent of our beautiful lesson for today. So hopefully that didn't take too long. Hopefully you're able to whip that homework out super quick. Remember, we're trying to do it in bite-sized chunks, right? We're not trying to be super crazy about it. Nice little bits and chunks of information, and then we'll put it all together at the end. So I think that's it. Fanfare music to get us out of here. I miss you. I hope you had a good notes day. Have fun with your homework. Bye.